Alright, so this video is going to be pretty quick. We want to discuss the properties of alkanes. And so those properties we are referring to are boiling point, melting point, as well as solubility. So remember, alkanes are basically just compounds that contain carbon and hydrogen. Okay, so only carbon and hydrogen, which means they are not going to be polar compounds. So they are non-polar compounds. Okay, and so that means that the only intermolecular forces that they generally have are going to be the van der Waals or London dispersion forces or instantaneous dipole. So those are all basically the same thing. And so we've got van der Waals forces, aka London dispersion forces, aka instantaneous dipole. Instantaneous dipole. Okay, and so remember, basically this is if we have a particular molecule, let's say this was just a cloud of electrons, and then the electrons are kind of moving around like this. At any given point, all the electrons could be maybe on just one side. And since they're negatively charged particles, this side would be delta negative, and this side would therefore be delta positive. And if we have another one of those spheres coming along, and we have a delta positive and a delta negative next to each other, the negative and positive attract, and so that's where we get our intermolecular forces. Now this only lasts for a moment, but when you have something, let's say in a flask, that's millions upon millions of molecules, and so this, even though it's only occurring for a split second, that split second times a million is going to be quite a bit of intermolecular forces that are occurring throughout that flask or beaker. And so this is going to impose some physical properties upon that organic substance, that alkane. And so remember, when we're talking about boiling point, specifically, there are a few key factors that we want to make sure that we remember, and that's basically if we can increase the surface area. So increase surface area, that means we will increase the boiling point, okay, and or increase the number of carbons and hydrogens. That's going to increase the boiling point as well. You can think of, for every carbon and hydrogen that's added, we're essentially adding more electrons, right? And if we're adding more electrons, then let me write that for you. So more electrons equals more opportunity for intermolecular forces. So I'll put let's see, VWF for van der Waals forces, just because your particular book has that, but I'll tend to refer to that force as instantaneous dipole, as I've written up here. Okay, but so basically, the more electrons that are present, then the more availability for those van der Waals forces to occur. And so this is basically seen if we have a general trend for this, for butane, for example, to, like, let's say we've got hexane. So the boiling point for this guy is equal to 0 degrees Celsius, and the boiling point for this guy is equal to 69 degrees Celsius. And that's because all we did here was add 2 more carbons, which obviously has a couple more hydrogens in there as well, right? But that's really all we did. Other than that, there's still the same forces that are the same intermolecular forces that are occurring within this, but just based on the fact that we have more electron density in this one, that's going to allow us to have more intermolecular forces overall. Okay, and another, obviously, the or if we're talking about intermolecular forces, if we want to compare, we can compare just to a polar compound. Remember, these guys are non-polar. Okay, obviously this guy is polar, and so generally polar compounds are just going to have a higher boiling point because they have more intermolecular forces. They're going to have hydrogen bonding or dipole-dipole, as well as, since they contain electrons, they are also going to have those London dispersion forces or those instantaneous dipole. And so the boiling point of this guy is significantly higher. So you can see the effect that this particular functional group has on the overall boiling point, because this only has 5 carbons, right? Whereas this one has 6 carbons and this one has 4 carbons. So yeah, that's just based off of the intermolecular forces, which is something we need to get familiar with. But another point we want to make about boiling point is that the more branching for an isomer, then the lower the boiling point. Okay, so again, we want to increase the surface area. Increase surface area for high boiling point. So this means that no branching is ideal. Okay. And obviously that's not necessarily always going to be the case, but the thing that has the least amount of branching is going to have the higher boiling point. Okay, so for example, if we have this guy versus this guy, okay, since this one has a larger surface area, higher surface area, it's going to have the higher boiling point. And that boiling point is going to equal 30 degrees Celsius. Okay, whereas this guy right here, he's very symmetrical, right? It's just, and remember from general chemistry that water forms a sphere because we want to increase the cohesive forces among those water molecules, and so it does that by decreasing the surface area so that the outer molecules of water have as much contact with the inner molecules as possible. Okay, so remember, a sphere is decreasing the surface area, so lower surface area, and so that means the boiling point is going to be lower, which is 10 degrees Celsius for this one. So at room temperature, this guy's flying up. This guy, I guess, kind of is a little bit, depending on how hot it is in the room. But hexane, for example, up here is a liquid at room temperature. So just a variety of points that we want to make about the boiling point, and that's it for now for the boiling point. But very related is going to be the discussion on melting point, and so I'll put melting point here, but we'll refer back to the drawings above. Melting point. Okay. Now, the melting point also is based off of intermolecular forces. Okay, so intermolecular forces play a role here, and that's because melting point is basically the point at which the solid material, which is tightly packed, close molecules, is becoming a little bit further apart into the liquid state, and so we have to break the crystal lattice, and that's basically a strong intermolecular force holding those things together. And so one of the key things to make sure that we have an increase in boiling point, so increase in melting point, is going to be caused by an increase in intermolecular forces. Okay, and so this can be done by, so increase in melting point can be done by an increase in the number of carbons. Okay, and that's basically going from butane to hexane. Okay, and so I'll just draw this guy again for you. So the melting point for this guy is equal to minus 138 degrees Celsius. And then the melting point for this guy, oh, look at you making straight lines when I don't want you to. All right, 1, 2, 3, 4, 5, 6. It's a lovely drawing, right? The melting point for this one, although it's still very low, is pretty high, a lot higher than minus 138, and it's at minus 95 degrees Celsius. Okay, so let's put that guy there. And then, just as our common example as above for the boiling point, we also had pentanol in there. So 1, 2, 3, 4, 5 with the OH there. The melting point for this one was minus 78 degrees Celsius. And again, that's because it has this polar functionality that allows for stronger intermolecular forces. Okay, so all right, so in that sense, its melting point is very similar to the boiling point, but for when it comes to the melting point and with respect to like surface area or symmetry, melting point is a little bit different. And so going back to this structure here compared to this structure. So remember, this one was spherical, so this one had more symmetry, had a lower surface area, and this one had a boiling point of 10 degrees Celsius, while this one had a boiling point of 30 degrees Celsius, right? And so let's take a look at the melting point. So the melting point for this one is minus 17 degrees Celsius. And so notice for boiling point, it went up for the structure on the right, yeah? But for the melting point of the structure on the right, it's actually minus 160 degrees Celsius. Now you might be thinking, oh, you crazy, right? But maybe I misspoke, like Steve Harvey did when he was announcing the Miss Universe. Sorry about it. No, that is correct. So that melting point is significantly lower for the structure on the right, because for melting point increases when we have increased symmetry. With increased symmetry. Holy moly. Increased symmetry. Okay, and so again, remember, when we form a solid material, is repeating units. It basically consists of repeating units called a unit cell, and that's basically most of the solids that we work with are going to be in a crystal lattice. Even if it's microcrystals and it doesn't look like giant crystals, they're going to have a repeating unit cell. And so that repeating unit cell you can think of as just like squares kind of next to each other, but then you stack those squares on top of each other. Okay, and so if we have, it's kind of like playing Tetris. It's much easier to stack things when you have like a nice symmetrical thing, like either a block or even a sphere. Like these spheres can fit nicely stacked on top of one another and make a really good unit cell. But if you have some like a weird structure, then it just doesn't make for a nice stack, right? And so I'm not even going to try and draw like a weird example of an oddly shaped thing trying to make stacks, but I think hopefully you get the idea that symmetry allows for better stacking, okay? Allows for better stacking, okay? And this basically allows us to form that solid much easier, and therefore at higher temperatures, and it takes more heat to kind of break it up into a liquid. Okay, now the last thing we want to talk about when we're talking about the physical properties of alkanes is solubility. Okay, now solubility remember it's like the golden rule is like dissolves like. Okay? And what that means is polar dissolves polar, non-polar dissolves non-polar, right? Okay, and so what did we classify alkanes as? Remember, alkanes are non-polar. So these are alkanes. And so if we're trying to dissolve alkanes, then we want to make sure that we have a non-polar substance. Okay, and so alkanes are also going to be considered hydrophobic. Hydrophobic. So remember, phobic is basically like a phobia, and hydro is like, whoops, sorry about that. Hydro is water, right? And so it's basically alkanes are afraid of water, and that's why we get an immiscible oil and water mixture. Whoa. Okay, and so remember, immiscible means that the two substances don't mix together, and that's why we get two layers when you mix oil and water. Okay, it's kind of like salad dressing. Yes, there you go. Put it all over my salad. Italian dressing only, please. If you like ranch, then we ain't friends. Okay. I worked in a restaurant for a while, and ranch is not okay. I'm sorry. Your ranch can wait. By the way, too. Be kind to your servers and bartenders. They got other things to do too. That actually reminds me. Totally on topic, I promise. But this is basically something I live by. But this is Danny Brown. He's hilarious. Good music too. If you like soggy cereal, then we ain't friends. Then I would cross that out because I actually like soggy cereal. Put honey bunches of oats in milk for a hot minute and gobble that right up. Yes, thank you. You can take bigger bites. It's really good. But I would insert ranch here. Come on now. It's just frustrating trying to serve 8,000 ramekins of ranch to people when you got other people to deal with. Anyway, I'm sorry, that was a little slight tangent, but I don't even know what we were talking about. We were talking about solubility. Yeah. So basically, alkane solubility needs to be follow the rules of like dissolves like, right? So we can't have it mixing with the water. You're going to get this immiscible two-layer solution, kind of like oil and water, or that delicious salad dressing, right? And so that means that we need organic solvents. So when we refer to organic solvents, or we might refer to them in a laboratory as the organic layer. Okay, so we could have something like a little container. Let's just say, I'll just introduce it right now. It doesn't matter. We would have a separatory funnel. Okay, so this is my best attempt at drawing that. I'm sorry if it's terrible, but basically what this is used to do something called extractions. And what you can do is you have basically an organic layer, and then you can have your aqueous layer. So, and since they don't combine, they form two layers, you can actually use this cool little separatory funnel. So separatory funnel, and this allows you to basically dissolve your organic substance in like the organic layer. Sometimes like things like caffeine, for example, they're soluble in organic solvents as well as aqueous or water, right? Because we cook them, or we brew our coffee and tea and water, but we can also extract it with something called methylene chloride, so CH2Cl2. or let's say ether or something, some organic layer. And so sometimes the organic layer can be on the bottom, sometimes it can be on the top. I just happen to draw it in this manner right now. And if they are separated in two layers, what we can do is combine them together, and the organic layer dissolves the organic substance but doesn't mix with the water. And then this can drip out the bottom, and you basically stop it when all the water goes away, and then you have your organic layer with your organic substance in there. And so it's really fun to do, actually, and it's really useful. So this will be done in a laboratory, either on a large scale or a small scale. In our lab, we do it on a small scale, also known as a micro scale, to do a variety of extractions throughout the year, but one in particular is of caffeine with methylene chloride. Okay. And so that's pretty much it for for alkanes. So remember, the boiling point is basically we want more carbons because we want more electrons to increase the intermolecular forces. And then we also want to have the least amount of branching, so that way we can have that higher boiling point. For melting point, it was the opposite. We want a highly branched system so we can perhaps get more symmetry, maybe. And more symmetry is going to increase the melting point. But then also increased intermolecular forces is going to increase the melting point as well. So you could have more carbons in that case. So, and then solubility, like dissolves like. If we're working with a nonpolar substance, we want to use nonpolar solvents or organic solvents. Okay, and so that's pretty much it.